SwayamPrabha. Digital India. Educated India.
Let us move on to the next problem. The major product formed in the following reaction. We are given a nitrobenzoic acid is given, para-nitrobenzoic acid. This is treated with the hydrogen at 3 atmospheric pressure in the presence of Rann and nickel at room temperature. We have 4 different products are given. This question was asked in December 2019. So if you look at the reaction, you can clearly understand there is a reduction reaction that is happening because we have hydrogen and the Rann and nickel. So what are the various possibilities that are given here? One, the entire aromatic system, the benzene system is completely reduced, that is given as 1, and that is saturated. The other one is like the carboxylic group is converted or reduced to the primary alcohol. The carboxylic acid is converted to the primary alcohol. In the other case, the nitro group is converted into an amino group. The first one also, the nitro group is converted to the amino group, and in the last one, only the nitro group is converted. Rest of the things remain the same. So we are going to see which one will reduce, the Rann and nickel will give the which product. So if we very carefully look at the reduction, the Rann and nickel will reduce alkynes, alkenes, nitriles, dienes, aromatics, and carbonyl group containing compounds. In the case of heteroatom bonds, it will also reduce hydrogens and nitro groups. So this is the most crucial one. So the Rann and nickel, it may reduce alkynes, and aromatics also will be reduced, but the only thing is under high temperature and high pressure. Okay, so that is the difference. Here it's just a 3 atmospheric pressure and it is room temperature. So these are all the 2 things which are not sufficient to reduce the aromatic ring. Otherwise, the aromatic ring also will be completely reduced to the saturated system if we carry out the same reaction under high pressure temperature in Rann and nickel. Since it is room temperature and 3 atmospheric pressure, aromatic system is not disturbed, so only the nitro group is reduced. In other words, our final product is this one. The rest of the molecule remains the same. So let us move on to the next problem. The major product formed in the following reaction is, here a ester and the carbonyl group is given in the starting material. We are reducing it using sodium cyanoborohydride at pH 4, that is acidic conditions. And we have 4 different products, A, B, C, and D. So this question is asked in June 2019. So if you look at very carefully what are all the products that are formed, we have a complete reduction of both the carbonyl and ester. Those products are given as A and B. And in C and D, only the carbonyl is reduced. And the only difference is whether the stereochemistry is the only thing that is different from these 2 systems. We can easily figure it out because sodium cyanoborohydride is a milder reducing agent, even milder than sodium borohydride. Sodium borohydride does not reduce esters. So in other words, A and B are not the required product. The only thing we have to look at is whether the stereochemistry is trans or cis. That is the only thing we are going to see here. So if you look at the sodium cyanoborohydride, the reduction of the carbonyl group is the only thing that is happening, and since the ester is below the plane, so obviously if you look at the ester is below the plane, so the hydride has to transfer from the top. In other words, the hydroxyl, when the hydride ion is transferred from the top, so the hydroxyl will go below. So that is the only thing. In other words, what is the CO2 ester's stereochemistry? In the same place, the hydroxyl is actually going to be there. So in other words, the final product is the one where the hydroxyl is also having the same stereochemistry. The reason why this happens is very simple to understand. Sodium cyanoborohydride is little bit bulkier. The bottom side is actually blocked by the ester unit. So the hydride ion can only approach from the top. So when the hydride ion approaches from the top, the hydride will be at the top. So the hydroxyl will go below the plane. So that is the reason here the cis product is the one that is formed in this reduction. And let us move on to the next one. The major product formed in the following reaction is, we are given some diol, and the diol is treated with MnO2 and this question is asked in 2018. So we have 4 different products that are formed in this particular reaction, and we have to find it out what is the actual product that will be formed. We know MnO2 will oxidize allylic system only. It will not oxidize the primary alcohol. So that is the one you have to keep in mind. So what is the allylic alcohol here? So this is the only allylic alcohol that is present here. So we can draw the structures as like this. The allylic alcohol is the one which will undergo oxidation in the presence of MnO2. So the moment we have an aldehydic unit and there is a lone pair of electron on the oxygen, so this will attack this electrophilic carbon, and then this will move towards this way, and we end up with a cyclic system. And since we have another same allylic system that is formed, this is a lactol, nothing but the lactol. So this lactol is still having the allylic position double bond. So this under MnO2 condition will further undergo oxidation to give the lactone derivative as shown here. So this is how we can easily figure it out, what is the product that will be obtained in this particular transformation. So let us move on to the next problem. So here the major product formed in the following reaction. So here a carbonyl group is given and we are using a zinc borohydride based reduction, and this question was asked in December 2013. So we have 4 different products, A, B, C and D, and if you look very carefully, the methoxy is retained only in A and B. In C and D, the methoxy is either lost or hydrolyzed to a hydroxy derivative, because zinc borohydride is a reducing agent. So the reducing agent will not hydrolyze the methoxy ether. So D is ruled out. And this will also not facilitate an elimination or similar type of reaction. So this is also ruled out. So we are left out with only 2 products, either A or B. The only thing is the stereochemistry is the only thing that is the difference in both the products. So we have to figure it out, what is going to be the actual product that will be formed. So like sodium borohydride, zinc borohydride also reduces the carbonyl group. So this carbonyl group is the only thing that will be reduced. But one caveat or one tricky thing here is zinc actually can chelate. So this is the major difference. The presence of this methoxy is the one that is tricking in this particular reaction, because if there is no methoxy, then it's very easy, straightforward way of identifying what is the product that will be formed. But the moment the methoxy is given there, so that is the extra trick. The question is actually telling you in the wrong direction, because mostly people won't look at the methoxy group while trying to answer this problem, because they will simply look at the methyl group. So the methyl group is pointing above the plane, so the zinc cannot approach from that plane, so it has to come from the bottom plane. So in that case, we generally give what is going to be the product very quickly, that this is going to be the product, like we will wrongly interpret. But this is not the product that is formed. The reason is presence of this methoxy group, because we have a zinc and we have an oxygen which has a lone pair, and we also have a carbonyl oxygen which has a lone pair. So when these two are there, they actually undergo reaction little bit differently, and here we end up actually with the anti-isomer and not the cis diastereomer. So the real change happens because of the presence of the methoxy group. So when you are going to solve these kind of problems, look for electronegative atoms with lone pair of electrons. They may, especially because here we are using zinc borohydride. If it is a sodium borohydride or if it is other hydrides, they may not actually get involved. But zinc is a transition metal, it has vacant d orbital, so this can coordinate with lone pair of electrons from both oxygen and the carbonyl group. So that is what is the differentiating factor in this particular question. So let us move on to the next problem. So the major product formed in the following reaction is, here we have a carbonyl group that is reacted with the sodium borohydride at 0 degree centigrade in methanol and THF. So we end up with the 4 different products, A, B, C and D. Okay, and if you look very carefully, we also have an ester group. Sodium borohydride does not reduce esters, So we can clearly rule out A and B as our product, because A and B cannot be the expected product, because both the carbonyl and the esters are reduced. Sodium borohydride does not reduce esters, so these are ruled out. Now we are left with only two products, either C or D. Now one is the endoside attack, another one is the exoside attack. So that is the only thing we are going to figure it out, how the reaction will actually take place. If you look very carefully, we have a gem dimethyl group at the bridge head. So that means something will prevent the approach of the hydride ions from the top side. So we have to now only look at from the bottom side approach. So we know sodium borohydride can reduce carbonyl groups and it does not reduce carboxyl groups. So these two are ruled out, and between these two, if the reduction of the carbonyl has to take place, the top side is actually protected by the presence of the gem dimethyl group. So the bottom side endo attack only will take place, and the endo attack leads to the final product, because endo, when we have the carbonyl here, the attack will take place from here. When the attack take place from here, the hydride will be transferred from here and the OH will go here. So in other words, this is how the product will be formed in this particular reaction. Let us move on to the next problem. So here the major product formed in this particular reaction, we have an alkyne and a carboxylic acid, and the reagent that is used is sodium and liquid ammonia and ethanol, followed by acidic workup. So the first step is nothing but the Birch reduction condition. This question was asked in December 2014. So Birch reduction means the aromatic system or the benzyl, the phenyl unit is going to undergo reduction. So we are going to get a 1,4-diene. That is what is going to be 1,4-diene is the one that is going to be formed in this particular case. Whether we have an electron withdrawing group. So this electron withdrawing group is on the alkenic carbon, as in either C or D or A or B. Of course, we know electron withdrawing groups does not stay on the alkenic carbon when the Birch reduction takes place. So we can completely rule out these two products. So these are not the expected product. So we only have A and B. So what is the difference between A and B? In both the cases, the carboxylic acid is in the ipso carbon, because this is the ipso carbon. There is no double bond in this particular case. So both are possible. The only difference is this is basically a trans addition. This is a cis addition. So that is because here we have an alkyne. So the alkyne undergoes reduction. Whether we get a cis product or the trans product is the one that is going to decide whether it is A or B. So if you look at the reaction, as we can clearly say, this is only the trans addition or the trans reduction is the trans alkene is the final product that is formed in this one, because in the previous couple of sessions ago, we had seen about the reduction reactions, Birch reduction reactions of alkyne bonds. So there we have clearly seen how, because Lindlar catalyst generally produces a cis reduction, but the Birch reduction produces a trans alkene. So that is what we have seen earlier. So keep that in your mind, so that it helps you in solving this particular problem here very easily. So the Birch reduction basically is a very regioselective and stereoselective reaction, and the ipso and the para position. So this is what is called as the ipso carbon. This is called as the para carbon. So these two carbons are basically electron rich, due to which the protonation actually happens on those carbon atoms. In other words, those carbons are going to have the hydrogen atoms, because these are electron rich. So they will have the hydrogen atoms, or the protonation takes place during the Birch reduction. So they do not have the double bond. Those carbons will not have the double bond. The rest of the carbons will have the double bond. Let us move on to the next problem. So here the major product formed in the following reaction. We have an aldehyde, we have a ketone, and we have sodium borohydride and CeCl3 7H2O, which is nothing but the Birch reduction conditions in the presence of methanol and water. So what is the product that will be formed? We are going to see here. So we have four different products, A, B, C and D. In A, both are getting reduced. So of course, Birch reduction is a very, very specific case. aldehydes are not reduced and only alcohols ketones are reduced. So here the aldehyde is also reduced, so this is not the product, and here we have some cyclic product that also will not form. And the rest of the cases we have, again in C also we do not have the we have the aldehyde group that is also reduced, so that is also not the possible case. So in other words, here it is a very straightforward, we don't even have to look at anything, we can directly say this is a final product because aldehyde is retained in this particular case in the Lucci reduction condition. So why that happens is simply because in the case of aldehyde, the cerium trichloride actually coordinates itself with the oxygen's lone pair, because cerium also belongs to the transition group metals. So there are vacant d orbitals, the lone pair from the oxygen is given to the cerium metal, so that is the reason they actually form the, this in a way protects the aldehydic oxygen. So that is the reason they do not undergo reduction under Lucci reaction conditions, that means sodium borohydride, cerium chloride, 7H2O conditions. So aldehyde remains intact, carbonyl, ketone carbonyl undergoes reduction by sodium borohydride. So one is protected by the cerium chloride, another one undergoes reaction. So this is how the whole process takes place. So we say this is a chemoselective reduction of ketones in the process of aldehydes. Identify, when we move on to the next problem, identify the appropriate reagent A and B in the following reaction. This question was asked in December 2011. So we have a acid, ester, alcohol. So we have a combination of acid, ester, alcohol, and they undergo some type of reactions, reagent A and reagent B, giving two types of lactones that are formed in this reaction. So in A we have lithium aluminum hydride, and in B we have boron dimethyl sulfide complex. This only are given in various combinations. In the other case we have the lithium borohydride and boron dimethyl sulfide complex. So we are going to see what are these reagents that will actually do. Lithium aluminum hydride generally reduces carbonyl groups, carboxylic acid, both acids, esters and amides, all of them are reduced by lithium aluminum hydride. Even nitriles, nitro groups, halogens are also reduced by lithium aluminum hydride. When we talk about the boron dimethyl sulfide complex, this actually is generally used for hydroboration reduction conditions, or this is also used in the case of reduction of carboxylic acid. So this is a very selective reagent for the reduction of carboxylic acid. And when we talk about lithium borohydride, this is very specific for reduction of esters, nitriles, primary amides, but they do not reduce carboxylic acid. So that means between BH3 boron dimethyl sulfide and lithium borohydride, we have selectivity. One reagent selectively reduces the carboxylic acid, another reagent selectively reduces the carboxylic esters. So we know what is the combination we have to use for identifying the product. So if we draw the mechanism for this reaction, you will easily follow that very quickly. So the boron dimethyl sulfide complex very selectively reduces the acid. So we have a carboxylic acid that is reduced to an alcohol. And once you have an alcohol, there is a lone pair of electron on this oxygen. So this will attack the electrophilic carbon, and then it undergoes to cyclization reaction. In the charge reversal step, the ethoxy group is lost. We end up with a lactone as shown here. So this is when we use boron dimethyl sulfide complex as the reagent. That acid is reduced. And what is the next one? When we use lithium borohydride, this reduces only the ester group. So it is exactly the same reaction but in the different direction. So the ester is reduced to the corresponding hydroxy derivative, and we have a electrophilic carbonyl carbon. The carboxylic carbon is the most electrophilic one. The lone pair of electron will attack this carbonyl carbon. So then it undergoes the cyclization as similar to the previous case, and in the charge reversal we can see the OH group is lost. Then we end up with the other lactone. So if you look at both the substrates, if we see the hydroxyl is on the right hand side, the carbonyl, the ester lactone oxygen is on the left in one substrate, the ester lactone is on the same side in the other substrate. So by changing the combination of the acids, whether it is the boron dimethyl sulfide complex or the lithium borohydride reagent, we can actually play around with what is the final product we are actually looking. And let us move on to the next one. The most appropriate reagent for the chemoselective conversion is, here we have a substrate which has a O-TBDMS group, O-acetyl group, and the N-BOG group. So these are all the three different groups that are protected. This is hydroxy protection, this is again the hydroxy protection, this is amino protection. So we have different four type of reagents are given, and we have only the acetyl group is converted to the, or acetyl group is deprotected to give the hydroxy derivative. Other two groups remain intact. So this question was asked in December 2012. We are given four different reagents. Let us look at what these reagents will do. HCl and ethanol and heating actually cleaves all the groups. N-BOC is cleaved, O-TBDMS is cleaved, and O-acetyl is cleaved. So that means there is no selectivity. So this is ruled out. And tributyl ammonium fluoride, when we TBAF, when we look at, this is mainly used for the cleavage of TBDMS group only. But in our product, the TBDMS is retained. So this is also ruled out. And potassium carbonate and methanol is a mild reducing hydrolysis reagent, and we only want the acetyl group to be cleaved. So this is the most suitable reagent in our case. And when we go to the trifluoroacetic acid and the ethanol water condition, it cleaves both these groups, but the ester group remains intact in that one. So this is also ruled out. So our reagent of choice for this particular transformation is potassium carbonate and methanol.